All right, now that we've examined the trapezoid and some of its properties, we want to be able to prove that a particular quadrilateral is indeed a trapezoid. So in order to prove that a quadrilateral is a trapezoid, we're going to show that it meets all of the elements, or it has what it takes to be a trapezoid. And that is, it has a pair of parallel sides. So if you're on the coordinate plane, you can show that two sides are parallel by showing that they have the same slope. If you're not on the coordinate plane, you might have to look for a pair of alternate interior angles that are congruent, or a pair of same side interior angles that are supplementary. Once you've proven that a trapezoid is a trapezoid, in order to show that it's isosceles, you can do this in one of two ways. You can either show that its base angles are congruent. Now on the coordinate plane, there's no real way to show that a trapezoid has congruent base angles. So while this way works really good out in plane space, it's not so effective on the coordinate plane. What does work real well on the coordinate plane is to show that your trapezoid has congruent diagonals. Okay, so let's go ahead and jump into this very first problem. It says, given quadrilateral ABCD with those vertices, prove that it's an isosceles trapezoid. I'm going to start first by proving that this guy or this fella is indeed a trapezoid. And remember, what makes a trapezoid is that he has a pair of parallel sides. So really, I'm going to look or use the slope formula to show that one of the pairs of sides is parallel. To get a really good feel for which pair of sides is most likely going to be the parallel sides, I am going to take a minute and sketch this fella on the coordinate grid. So there's point A, there's B, C, and D. So from my sketch, it looks like the pair of parallel sides is most likely going to be the top and the bottom, side CD and side AB. Remember, anytime you use a formula, you need to write it down. So slope formula is change in y over change in x. And the two segments I want to find slope for are segment AB Now I'm pretty good with the mental math. If you're not, grab your calculator and type this whole entire expression into the calculator. It's going to tell you 0 over -9, which gives us a slope of 0. And considering the picture, this flat horizontal line, it is not at all surprising. In fact, it's expected that that slope would come out to be equal to 0. And now I want to go do the same thing for segment CD. And again, I'm pretty good with the mental math, but if you're not, grab your calculator and type this entire expression into your calculator and let your calculator do the work for you. And again, as expected, the slope of that segment came out 0. And so now we need to write a little blurb about why these calculations do indeed make our quadrilateral a trapezoid. So I know that they're parallel because they're the same slope. So I'm going to write a little bit about parallel lines have the same slope, or segments with the same slope are parallel. So this makes segment AB parallel to segment CD. This quadrilateral has a pair of parallel sides. Which makes it a trapezoid. So now that we've proved this fella is a trapezoid, now we have to prove he's isosceles. And again, we can do this one of two ways. We can either show that his base angles are congruent, but on the coordinate grid, that's really, really, really hard to do. So I'm going to instead show that his diagonals are congruent. And we know that segments of the same length are congruent. So we're going to find the length of the diagonals by utilizing the distance formula. And the two diagonals are diagonal DB and remember, when I type the distance formula into my calculator, I start with the very first open parentheses, but I do not substitute in the square root sign. So this tells me that what goes underneath the square root sign is 100, and the square root of 100 I know is 10. And now I'm going to go ahead and find the length of diagonal AC. And again, when I type this into my calculator, I'm going to start with the open parentheses and type in everything that comes after that open parentheses. My calculator tells me that the value of what's underneath the square root sign is 100, and the square root of 100 I know is 10. So now I have to write a little blurb about why these calculations make my trapezoid isosceles. So this trapezoid has congruent diagonals, making it isosceles. So that's how you'll deal with a trapezoid question if you see one on the coordinate plane. The next couple of examples, though, deal with plane space. In example 2, we're given this isosceles trapezoid ABCD. What I'm going to do is go ahead and outline this fella in green just as a reminder to myself that he's an isosceles trapezoid with bases that are parallel AB and DC. And our goal or our mission is to prove that triangle CDE is itself isosceles. Well, I know that if this green trapezoid is isosceles, I know that base angles A and B are congruent. Because bases DC and AB are parallel, I know that the angles that correspond with A and B also have to be congruent to each other. And now I've got those two base angles in my triangle that are congruent to each other, which forces my triangle to be isosceles. So that's kind of the gist or the direction that my proof is going to take. So I'm going to go ahead and start out with isosceles trapezoid ABCD. That's a true statement because it's given to me to be a true statement. And because that's a true statement, I know that base angles A and B have to be congruent to each other. And the reason is that the isosceles trapezoid has congruent base angles. I'm now going to go ahead and I'm going to use those parallel lines, and this is why it's important for you to be able to recall all your knowledge about parallel lines and use the properties of parallel lines to establish a couple other pairs of angles. I know that angle A is congruent to, I can't call this one angle D because there's multiple angle Ds, so I'm going to say angle EDC, and I know that angle B must be congruent to angle ECD. And that's because parallel lines have congruent corresponding angles. And now I'm going to pull a little substitution here. I'm going to plug in angle EDC over here for angle A. And I'm going to substitute angle B with angle ECD. You heard me use the word substitute, so it won't come as any surprise to know that my reason there is substitution. So at this point, what I've done is I've established the fact in my proof that those little red angles are congruent. And if that little purple triangle has those red angles that are congruent, I know the sides opposite those angles must also be congruent. So this is where it's critical that your proofwriting skills about triangles are top-notch as well, because we're really going to be pulling together everything we've learned and used so far with respect to all different types of proofwriting, parallel lines and triangles, and we're going to be building on that knowledge. So when two angles of a triangle are congruent, the sides opposite those angles are congruent. So we haven't used that one in a while, but you still need to know it. And because that triangle now has a pair of congruent sides, he must be isosceles. And that's because a triangle with two congruent sides I think that at this point, due to time constraints, we're going to go ahead and skip number 3 for the time being, because I do want you to have some time to kind of let things roll around in your head and think about what you just saw and heard, and take some time to, as always, in your own words, summarize the key ideas and important takeaways, and then see if you can apply what you know in order to solve the two problems on page 8.